Okay, first of all, I just want to thank the Petroleum Engineering Association and all the participants who have entered this course. And I hope that after we finish talking about this course, that all the participants will have information about how to dealing with XRD and for XRF and for the scanning electric microscope. So before we will talking about XRD and the XRF and the scanning electric microscope, we shall say what we want to talk about in this course. We will talk about the introduction, what is the meaning of the XRD, and how to use the XRD in the mineralogical classification, how the XRD works, what is the application of the XRD, and what is the meaning of the XRF, how to use the XRF in the chemical classification, and what is the application of the XRF, and how the XRF works, and the meaning of the scanning electric microscope, how to use the scanning microscope in studying the shape of the sample under microscope, and how does the scanning electric microscope work, and finally, what is the application of the scanning electric microscope. So before we talk about the XRD and the XRF and the scanning electric microscope, we shall give more introduction about this course. So this course is subjected to all the geologists, and all the geochemists, and all the person who are interested in knowing the chemical and the mineralogical, the shape of the minerals inside the rocks, because in this case, you will have full distribution or a full description about the rocks that you're dealing with. Because we will, sorry, but I had a message, we will back to our talking. So after you knowing the chemical and the mineralogical and the chemical and the mineralogical of the rocks, in this case, you can know which type of rocks you are dealing with. And because we know that there is 3 types of rocks, starting from igneous rocks, metamorphic rocks, and sedimentary rocks. So after knowing the chemical, the mineralogical, the shape of the minerals inside each rock, you will be able to know what rock you're dealing with. So suppose that we was working with kaolin, for example, and the kaolin have 2 grades, called the low grade kaolin and the high grade kaolin. So in the case we have known the chemical composition of the kaolin we're dealing with, so in this case we can know in which industry we can use the kaolin we have. Suppose that if we want to use the kaolin in brick industry, or using the kaolin, for example, in ceramic industry. So this is the most important thing about knowing the chemical and the mineralogical and the shape of the minerals inside the rocks. And we shall know that the rocks in the nature are made of 2 or more minerals. These minerals are composed with each other to form for us the rocks. And these rocks are mixed up and through what's called the geological process. So we need to know what is the meaning of the geological process. The geological process, it can be known as the event that occurred on the geological time scale, which can be ranges between millions of centuries, or hundreds of meters, or hundreds of kilos. And we have to know that the major geological process we have is called the impact, volcanisms, tectonisms, and erosion. After you have known how to use the XRF and the XRD and the scanning electric microscope techniques, you will have the ability to identify the rock type you're dealing with. So this was a small introduction about this course. Now we will start talking about what is the XRD and what is the meaning of the XRD. So the XRD means X-ray diffraction. And the XRD can be one of the most important techniques in order to know the mineralogical characteristic of each sample we have, and in order to identify and classify the mineral. And it is known as a commonly and probably techniques for all the geological application. So in order to make a sample for the XRD, the sample should be very well grounded by using what's called the mortar or the pickle. The powder must be very fine. Why it should be very fine? In order to avoid the fractionation of the powder minerals. Then the sample is mounted into a sample holder, and this sample holder has a thickness between 2 millimeter thick aluminum plate with a 20 millimeter square hole in the center, and then a glass of microscopic slide were used in order to pack the powder and put it inside the X-ray instrument. And the sample of the XRD should be between 2 to 5 grams. And from the slide here, we can see that there is an X-ray or there is an XRD instrument. And this XRD instrument called the D4 intravertebral X-ray instrument, which there is a lot of X-ray diffraction, or there is a lot of X-ray instrument we use for identification the mineralogical inside the sample, but all of them work the same. So suppose that we make the sample here, and we have this sample which is coming from the X-ray analysis. So how we can now identify the sample we have here, and what is the meaning of 3 stars, or what is the meaning of 2 stars, and what is the meaning of 1 star. For each sample, we make a classification on the XRD, have what's called the lesion here. So we can see that the Q is according to the quartz, and K is according to the kaolinite, and S is according to, and S is for the smectite, and M-I is for the milkovite and elite. So what's the meaning of the major, and what is the meaning of minor, and what is the meaning of the trace? So when we go to the graph here for the X-ray analysis, we can see that the major elements we have inside the analysis have a high peaks here. So you can see the quartz has a high intensity peaks. So this means that this sample is a major in the XRD analysis. And also, if you can check the quartz here, you can see also it has a high intensity peaks that we have here. But if we make a comparing between the quartz here and the kaolinite here, we can see that there is a difference between the intensity of the peaks between the quartz and the kaolinite. So that's why the quartz has shown us a high intensity here. And the kaolinite here has shown a less density peaks that we have here. But if we check for the smectite or the muscovite, for the smectite, we can see there is a little bit of intensity here. It's a little bit, it's not as the quartz we have here, or either for the kaolinite we have here. That's why it's called a trace elements, because the trace element here don't have this high amount of intensity we have here. So that was how we can make interpretation for the result we have it from our XRD by showing or by knowing which minerals have the intensity of our high peaks that we have it inside the sample. And also the XRD can show us the relationship between the d-spacing and the intensity here. It's called the intensity, and here the d-spacing. So from this graph, we can make a small interpretation for our minerals that we have inside each sample. But to be honest, one sample is not enough for identification or for knowing the results we have it on the XRD. So you need at least from 5 to 10 samples in order to know exactly what the minerals you have inside the materials. This sample was for kaolinite materials, and it has shown us what the major elements and what is the minor elements and what is the trace element we have. But if we see the calcite here has not been shown in the X-ray diffraction because there is no peaks for it. So in this case, we will not have any of calcite materials in this sample. So this was a small brief about how we can make interpretation for the samples under the X-ray diffraction. And as I told you before, we need to make more than 10 or 15 samples in order to make accurate about the minerals that we have here. So now after we make small interpretation for the results we have, we shall know how this XRD works. So how the XRD works, All of us, we know that the X-ray is used to investigate of the crystalline materials. This will mean that all the crystalline materials will have one thing in common with their components. And what they are then? They are the atom, the ions, and the molecules. They are arranged in a very regular manner. So this is a necessary requirement for the XRD in order to occur. Let us ask one question. What if happened if the X-ray are scattered by periodic arrays of particles with long order? In this case, what will happen? The scattered X-ray from the sample here will make interface with each others. This means that the detectors of the XRD can only read out a signal. It will read only the signal at angle where the interface is occurred. And here we can see that there is a lot of dots in this graph. And all of these dots are corresponded to the building block of the crystalline materials. And because of the crystalline materials, the atoms are arranged in a very predictably way from here. So this means that the incident X-ray beam, which is coming from the X-ray, is scattered at different planes of the material. So this result will diffracted X-ray. So therefore, they will have a different optical path length to travel, and also the magnetic of the path length only will depend on the distance between the crystal plane of the incident engine of the X-ray beam here. So this will lead us to what's called the Bragg's law. So the principle of the X-ray techniques is depending on what's called the Bragg's law. So what is the meaning of the Bragg's law and what is the depending of the Bragg's law? So the Bragg's law here, in order to have the Bragg's law, what is the meaning of the Bragg's law? That the X-ray are scattered from a crystalline lattice. This is the crystalline lattice we hear. So the peak of the scattered intensity will absorbed. And in this case, we will have two conditions in order to have the Bragg's law. It's called the angle of scattering and the path length difference we will have here. And the condition to make the Bragg's law of the maximum intensity in order to calculate details about the crystal structures. So in this case, we will deal what's called the Bragg's law. The Bragg's law here is called n lambda is equal to 2d sine theta. So what is the meaning of n and what is the meaning of lambda? And what is the meaning of d? So from this equation, we can say that n is the different order, and all the time it's called the first order, and it's also called and order is equal for 1. And lambda is the wavelength of the rays here. And also we deal with what's called Cu kappa alpha. And we say, and we tell you in the next slide why we deal with the Cuak alpha. And we will back and say that L lambda is equal to 2d sine theta. So the wavelength here is according to the Cu kappa, which is equal to 15406 angstrom. And then we say that it's a different order. And the d here is the spacing between the layers of the atoms here. And the angle here, the angle between the incident ray which is coming and the surface of the crystal we have here. So by knowing the angle, and by knowing n, and by knowing the wavelength, we can calculate the d-spacing we have here. Because all of things we have, because we know everything, the other thing and the thing we don't know is the d, which is called the d-spacing. This is the d-spacing between the atoms. So this is the principle of how the Bragg's law are working. N lambda is equal to 2d sine theta. But here, why are we dealing with Cuak alpha? Why didn't we deal with other one? Because the kappa K is an X-ray energy frequently used as a lab scale X-ray instrument. The energy of this Cu kappa is 8.04 Kelvin. This can be which corresponded to an X-ray wavelength 1.5406 angstrom. It can be used in the X-ray because it given the shortest wavelength, which is above 1 angstrom. And because of their short wavelength, and because of their both scatter weakly and contract the diffraction. So that's why we use the Ca copper. All the scientists say that the K alpha is more intensity than the K beta. Why? Because the copper targets are easier to cool than most other possible electrodes. That's why using the Ca alpha as the wavelength in the X-ray diffraction, so the most reference has candidates on the Cu copper alpha, so it easier referred to other results. So that's why we use the Ca alpha in dealing with the X-ray diffraction or for the X-ray methods. Here, what we call the X-ray peaks. From this graph, we can see here is the intensity we have, and here is what called the 2 theta, which means the angle detector observed intensity. So the XR peaks here can give us what called the peak position, which is equal to despacing, the phase identification, and which happened in the change in the latitudes that we have and the atomic substations. But when we going here for the antidote intensity, which is equal to the percent of the crystalline we have, and the quantitative analysis. And here, the peak width, which is equal to the crystalline preferences and the crystalline size we have here. So this was a brief about the XRD, how to make interpretation for our result in the XRD, how the XRD works, and what is the diagram of the XRD. Where we can use the XRD, or what is the XRD applications? We can see that the XRD application is for determining the structures of the crystalline materials, determining of the electron distribution within the atom and through the unit cell, and also determination of the orientation of single crystal, and measuring of the strain and small grain size, and finally determination of the texture of the polygranated materials. After we have said about the XRD, now we will go to talk about XRF. So what is the difference between the XRD and the XRF? The XRD are used in order to make mineralogical classification. But the XRF are used to make the chemical composition. And the XRF are quantitative measurements. So the XRF means the X-ray fluorescence. And because all of us know that the rocks have chemical composition, so the XRF used in order to determine the chemical composition we have. So the chemical composition of the rocks guide us to identify the rock types with many information, because it will give us quantitative about the major oxide we have here. So most of the rocks are referred to the silicates group because we have a lot of groups, but the major groups, the silicates. So the most of rock silicate groups that contain of major oxide of silicon and the other oxide. So the X-ray analysis is the most accurate instrument in order to determine the major oxide in the rock. Now, how we can make sample for XRF? We have to main ingredient a sample into a final powder, ideal to a grain size which is less than 75 nanometer. Mix it with a blending and then mixing the mixture between 20 and 30 temperature in order to produce a homogeneous sample pellet. And the sample size for the XRF should be 7 grams in order to have a lot of information and also in order to have a lot of the quantitative materials on the XRF analysis. This is type of XRF machines that we use and we call the Barker Axis XRF or Pioneer. There is a lot of XRF instruments, but this is one of the instrument we use it for the XRF. Okay, suppose that we have this result which is coming from the XRF. And we say before that the XRF is depending on the major oxide that we have inside the materials. And all of them should have 100%. So here we can see that the SiO2 have large amount. So this will call major, which I mean the SiO2 here has the high amounts. And we can see here that the TaO has the less amount. But as I said before, we need to make more than 10 or 20 samples in order to identify the major oxide we have. This was a brief about how to identify the result of XRF that we have. So, and this samples is referred to the kaolin materials. And why we say kaolin? Because in the XRD before, we have identified the materials as kaolin. So here, we make this analysis for this kaolin samples and have shown us the major oxide, we have it inside the sample. And we can, after this, compare this result we have with the typical analysis for the minerals that we are looking for. And this will help us as industrial geologists in order to know which industry we want to go with it. So if we want to go with the bricks industry or for the ceramic industry, so we need to make what's called the beneficiation for the major oxide here in order to increase the aluminum or in order to decrease the silicon to be used as it is for the ceramic industry or for the other industry that we are looking for. Now, how the XRF works. This is a graph for the XRF processes. So an X-ray beam with an energy, enough energy, affects the electrons here, the inner shell of the atoms. So in the sample is created by what's called the X-ray tube inside the handheld analyzer. So then the X-ray beam is emitted. You can see that the X-ray here will be emitted from the front end of the handheld X-ray analysis. And what will happen that the X-ray beam then will have to interact with the atoms in the sample by displacing electrons from the inner orbit shifts. Here is the orbit shells we have. As a result, this displacement will occur as a result of the difference in the energy. So we will have a difference in the energy between the primary X-ray, which has been emitted, and the X-ray which is coming from the analyzer and bending energy that hold the electrons in their property orbits here. So the main function of the XRF is depending also on the X-ray and how the X-ray are emitted and how the X-ray is going into the sample and how it's emitted the energy and it's how it can affect the orbit or the shells for the sample that we have. What we can use or what is the XRF application here? XRF application can be used in the geology, in the fuel industry, in the food chemistry, and also it can be used in the art science. For example, if we want to do the XRF analysis for the food industry, so it should determine of the toxic materials that we have. And on the fuel industry, it is monitoring the amount of the contaminated in the fuel. So the XRF also is a very important application for the geologists or who are working in the petroleum industry. So this is the main function or the application of the XRF. Now we will talk about the SEM and what is the meaning of the SEM and why we using SEM. So the SEM here is meaning the scanning electron microscope. And the SEM is a very unique tool for studying the materials under the microscope. Why? Because it gives us information about the fabric and about the shape and about the size and about the crystal habits that we have between the boundaries of the materials inside the rocks. And this shows us an instrument that we use it for the scanning electric microscope, which is called FLE Quanta 200 scanning electric microscope instrument. And as I say before, there is a lot of instrument for the scanning electric microscope. So if we have this sample and we want to identify the result of this sample, how we can identify? This sample is referred to what's called the kaolinite materials. And how I know it is a kaolinite materials, because the shape of the particle under the microscope is showing as what's called hexagonal. The shape of it, it's hexagonal. And why we going to the scanning electric microscope? Because we have do before the XRD, and we have do the XRF. After we do the XRD and the XRF, we have identified this result of this sample as kaolinite. So we take this sample and we put it under microscope, and we know the shape of it is kaolinite, and you can see here how the crystal habits are between them. What I want to say also, that in order to know the shape of the crystals inside the microscope, you need reference for the book for the shape of all the crystal under microscope. And after that, you will take this sample and put it under the microscope and study it under the microscope to see what the minerals you look for it. And the scanning electric microscope can also be a very, very important instrument for all the geologists, for the geologists, for the geochemists, for the industrial geologists, in order to know which the fabric they're dealing with. And finally, today, we will talk about how the scanning microscope works. But before we talking about the scanning microscope, we need to know what is the main component of the scanning electric microscope. First of all, we should have what called the source of electrons, column down, which electron travel with electromagnetic lens. Here we have what called the electroconductor, a sample chamber, and finally a computer and display to view the image. Okay, this was the main component for the scanning microscope. So how the scanning microscope is work? You can see that the electrons are produced on the top of this column here. Where is the mouse go? Here. Of the column. So here it will happen that an accelerated down and pass through a combination of lens and aptitude to produce what called a focus beam of the electrons, which hit the surface of the sample. The sample here should be mounted on a stage in the sample area, unless if your microscope is designed at low frequency. So here we can say that both the column and the chamber is depending on the what called in the vacuum pump. So the level of the vacuum pump will depending on the design of your microscope that we have. And the position of the electron beam on the surface is controlled by scan cools. There is a scan cools inside the scanning microscope. This is set above the object lens. So this will allow the cools of the beam to be scanned over the surface of the sample. This is how the scanning electric microscope works. And finally, here we'll say what is the application of the scanning microscope. We can say that it's for image composition and some bonding difference. It can also help us in view the frozen materials, and finally it can help us in generating the X-ray from the sample for microanalysis, which called the EDS. And if you want us to talk about the EDS in another presentation, we will talk about the EDS in the other presentation, because this is a very important subject. So that's what a brief about the scanning electric microscope, the XRF and the XRD, and how we use them in our geological application. Now I have finished my presentation, and we are waiting for a question for the participant if they want to ask anything. Participant, if you need to ask anything, I am here. Participant, if you need to ask anything, I am with you. Participants, I think there is no any answer here. Okay, we have finished our small presentation about the XRD, the XRF, and the scanning electric microscope. And we will wait for the answer for the participants here if they want to ask anything about the XRD, XRF, or the scanning electric microscope. Here I have one question that how I can calibrate the XRD and XRF machines. Okay, this is very good question from Karina Franco. In order to calibrate the XRD and the XRF machines, first of all, you need to know what materials you have to deal with that. Calibration of the XRD, depending on what you put as a reference in your sample for the XRD, and then you can make the calibration according to the manuals you have, because each mineral have their own calibration. XRF is different because XRF is a quantitative materials, and there will be a lot of samples we put it in the XRF in order to deal with the sample we have. Another question, Cranio Franco, if you need more question, just send me on LinkedIn and I can answer for you what you need. Anything? Any question, participant? Participants, is there any question? Is this information was very good for you? No, I mean standard samples, standard samples. Mr. Franco, if you need another question, send me and I will give you all what you need. Okay, in the Bragg law is the different order. In the Bragg law is the different order, and also it can also for the first orders is equal for number one. It is effectively for heterogeneous rock sample. Which one and then which one it you mean is affected for homogeneous rock sample? The XRD or the XRF? No, when I was working on the XRD before, I need to separate the minerals what I'm looking for, because I was looking for kaolinite materials, so I have to put the kaolinite materials alone and make analysis for this kaolin materials. And for the analysis for the rock, it should be solid samples in order to deal with XRD and the XRF. Okay, XRF, the AAS is called this. The AAS is called for the concentration for the trace elements, because it in the AAS you need to use like CH4 and HCl, and to make it as liquid materials and put it on the instrument in order to know what is major trace elements you have. The AAS can give you more accurate result than the XRF, because XRF is dealing with major oxide, and the AAS can dealing with the trace elements.